Thank you again to our second round of Lightning Talk presenters, another great round of user stories. To kick off our third and final round of Lightning Talk presentations, I'd like to introduce Erik with Saildrone.
Okay, I'm Erik Chubb. I work for Saildrone. We build the drones that you see in this picture. We operate them, and then our product is really the data that we collect. So we sell the data. We do ocean science like dissolved CO2, bathymetry, which is ocean floor topology, and then we also do security on the ocean. So that's basically pictures. Next slide. The project that I'm working on is that given a location and time of year, predict the solar power generated by one of our drones. Next slide. So the concept is pretty simple. On the y-axis here, we have the actual power generated by a drone somewhere in the world, like at a time and location. And then on the x-axis, we have the irradiance from NASA power at that same time and location. So we plot the two against each other, get our best fit coefficients, and then we can use those best fit correlation coefficients to make predictions. Next slide. One unusual aspect of our project is that it's mobile. So you can see the on the right there's the blue drone GPS track. And of course, as we're moving through the world, we need to pick the NASA power bin that is closest to wherever we are. So those are the pink dots there. So we have a function that wraps the API, or actually NASA the AWS system, to get us the closest relevant data. Slide. So one of the products that's useful internally at within Saildrone is making seasonal predictions of the power that we will generate. So given that we have the best fit parameters that I talked about 2 slides ago, and we have the hourly NASA power data from the last 21 years, we can make a prediction at a particular location over the course of the year. Next slide. So on the y-axis here, you've got the power generated, and on the x-axis, you have the time of year. And I want to draw your attention to the solid orange line. That is my best guess at how much power a drone operating at this location in the Southern Ocean, south of Africa, will make during the year. So the generation in itself is pretty useful, but it's even more useful if you add the load. So that gray line there is the load that we expect to be using, and load is dependent on like our sensor suite and other things. Next slide. So once we have the load and we have the generation, then we can do things like what's shown here on that center vertical line, which says starting on September 28th, solar generation is expected to cover the load. And then if you continue through the year and then to the beginning of the next year, then you see the first week in March, the generation drops below the load again, and that means that we need to get out of that area because we don't have enough power to run the system. Or we need to turn off sensors, something like that. Next slide. So NASA's power has been critical to building this tool. Clarity on power generation is useful in several contexts. Often during business development, we ask ourselves, can we support this particular mission, in this part of the world at this time of year with this sensor set? And if not, then how can we modify the contract so that we can? Or will turning off an unnecessary load be enough to succeed at the mission? And then once we get to mission planning, sometimes we have questions like, if we add 5 watts, how much does that change our operating season? And we can answer those questions now. And then if we know how much power we should be making and how much power we are making, you can actually monitor the health of the solar system that we have. And then, of course, it's nice for assessing engineering trades. Should we be putting resources towards like adding solar to the vehicle, or should we be putting resources towards reducing loads? And we can make quantitative answers to questions like that. So thank you very much, NASA. That was great. Or it's great to have the resource.
Thank you, Eric.